So in this lesson, we're going to be talking about exponential and logarithmic functions, specifically logarithmic functions, which are the inverse of exponential. Being that they are inverses of each other, they share some characteristics. So if we go with a general exponential function, a to the power of x, then some reference points that we can use to help graph it might be -1, 1 over a, 0, 1, and 1, a. When you go to the inverse, log base a of x, then those x and y values are inverted. So we have a 1, 1, 0, and 1 over a, comma, -1. Likewise, the asymptote is switched from y equal to 0 to x equals 0 for the inverse. And domain and range is also flipped, because when you switch x and y, or the domain and range switch as well. So we're going to look at some examples dealing with the inverses of exponential and logarithmic functions. In this example, we're supposed to find the inverse of y equals log base 7 of, in parentheses, x plus 1, then outside my parentheses, minus 3. When we go to find the inverse, we're going to start by switching the x and y. So instead of y equals, it's going to become x equals log base 7 of y plus 1 minus 3. Then the general approach to solving logarithm equations is to get rid of the stuff outside. So we'll add 3 to both sides. X plus 3 is, well, just x plus 3. We can't actually do it. Equals log base 7 of y plus 1. Now the inverse of a logarithm is making both sides an exponent of the base. So the opposite of log base 7 is making both sides an exponent of 7. Since exponents are 1 to 1, this is one of the properties that we can apply. 7 to the power in log base 7 will cancel out. On the left side, we can't actually do anything with it, so we'll just stay 7 to the power of x plus 3 equals y plus 1. Still have to finish getting y by itself, so we'll subtract 1 from both sides. And again, due to the exponent, we really can't do anything with this. So 7 to the power of x plus 3 minus 1 is equal to y, or in other words, y equals 7 to the power of x plus 3 minus 1. So in this next example, we're going to be finding the inverse of f of x equals 2 to the power of 3x minus 1. And then after the exponent, we have a plus 3. So remember that f of x means y equals, or specifically y. So when we start finding the inverse, we're going to switch x and y. So it's going to become x equals 2 to the power of 3y minus 1. And then we have our plus 3 off to the side. Now we just have to solve for y, so we're going to get rid of anything that's not a part of the exponential. The exponential is this, the number and its exponent. So we will subtract 3 on both sides, and x minus 3 is just going to be x minus 3. Now we need to get rid of the base. Remember, to cancel out the base, we use a logarithm. So we are going to do log base 2 on both sides, putting stuff in parentheses. On the right side, log base 2 and 2 to the power cancel. So we have log base 2 of x minus 3. We need the parentheses because there were 2 terms. Equals 3y minus 1. Then it's a two-step equation from here, so we'll add 1 to both sides. So log base 2 of x minus 3 plus 1 equals my 3y. And to finish getting y by itself, we will divide both sides by 3, giving us y equals log base 2 of x minus 3 plus 1 all over 3. We really can't simplify anything with this. However, there are a few different ways we could rewrite it. So some common ways that you might see would be putting log base 2 of x minus 3 over 3, and then plus 1 over 3, so that might be one of them. They might also use f negative 1, which means the inverse of f. You may also see f negative 1 of x, or y equals, of 1/3 log base 2 of the difference of x and 3 plus 1/3. And bizarrely, at this point, this may not make sense, but hopefully later it will. You may also see log base 2 of x minus 3 to the 1/3 plus 1/3, or f negative 1 of x equals log base 2 of the cube root of x minus 3 plus 1/3. So these are all different variations of writing the same thing. These last two may seem a little bit strange, but when we talk about logarithm properties later, they should make a little bit more sense. But there are possibilities that you may see when you check answers for different problems. Okay, so in this example, we're going to be graphing the function f of x equals log base 2 of the sum of x and 2. We're going to state the domain, range, and end behavior. Now, this is a log function with base 2 as the general parent function, which means some order pairs that you can apply transformations to help you out would be 1 over a, or 1 over 2, comma, negative 1, 1, comma, 0, and 2, comma, 1. To emphasize where these are coming from, remember that if our base is 2, well, log base 2 of 1/2 is negative 1. Log base 2 of 1 is 0, because any number to the power of 0 is 1, with the exception of 0. And then log base 2 of 2 is 1, because 2 to the first power is 2. And also the asymptote, which normally is at x equals 0. Now, we're not going to use the fraction one, but sometimes you can use, or sometimes you might need an extra point to help you graph the shape. But we're going to skip over the fraction one and then just apply our transformations. So same rules I usually use for transformation is if the operation is happening inside, it affects the x values, but in the opposite way. So we see x plus 2, which means we're going to be really doing x minus 2 as our transformational rule. And if it's outside, it will affect the y values, and in the same way. There's no operations, addition, subtraction, multiplication outside, so nothing's going to be happening to y in this particular problem. We're going to apply the transformation here to just our x values. So take our x values and subtract 2. 1 minus 2 is negative 1. 2 minus 2 is 0. And the asymptote x equals 0 will become x equals negative 2. The y values are not changing because we do not have any transformations happening to the y. No operations on the outside of the logarithm. So there we have the information we will use to graph. And we are accidentally zooming in. Yay! There we go. So information we will use to graph right there. Plotting the asymptote first, just because I like to do that. So x equals 0, or x equals negative 2 is a vertical line where all the x values are negative 2, mainly right here. 0, 1 is the point, 0, 1 right there, and negative 1, 0 is right there. Now, to graph this, when I graphed exponential, in order to know how to draw the shape in, I looked at which point was closer to the asymptote, and then I started on that side. So in this quick little example up on the top right, the left point is closer, so I start on the left, curve through, and then go through the points. Hug the asymptote and curve through the points. The same thing is going to be happening here, but we're going to look at the higher point or the lower point. Which one is closer to the asymptote? Well, the lower point is, so we start at the bottom, hug the asymptote as best as we can, and then curve up and out. And there we would have the shape of this logarithmic function. Okay, and the next part that we're going to look at here is stating domain, range, and behavior. We're going to also describe the transformations. So domain for a logarithmic function normally is, for the parent function, it's normally x greater than 0. However, we have a transformation of subtracting 2. So even without looking at the graph, we can see that is going to be x values that are, well, if we subtract 2 from 0, we get negative 2. We're not multiplying or dividing by a negative, so the inequality sign will stay the same. So it will just be x values greater than negative 2. And if we check the graph, here's where x values are negative 2, and you can see that we have the graph only on the side that has x values greater than that. Range for a logarithmic function for the parent function is all real numbers. And, well, no matter what transformations you apply to all real numbers, it will always be all real numbers. So domain and range for this function, domain x is greater than negative 2, and range is still all real numbers. Now let's talk end behavior. End behavior is a little bit funky with this. So end behavior partially depends on what type of definition you're using as end behavior, because different people will say different things about end behavior I've found in the past. Some standardized tests will say one thing, also try to get at one point where others won't. So I'm going to kind of describe both of them. The typical definition that I teach is that end behavior is what is happening to the y values as x approaches either positive or negative infinity. So as x goes to the furthest most extremes. So we've been typically looking at left and right end behavior in that regard. So I'm going to actually start with right this time. So when I do end behavior, we want to start in the middle and go off to the right as far as possible. And the graph should either go up, down, or level off. This one goes up on the right side. Now, if we try to do left side, we start in the middle and go to the left. It appears like it's going down. However, there is a little bit of a problem with that idea. We never cross this asymptote. End behavior is defined as we go to positive or negative infinity. So all the way down here and even farther than what my graph depicts. But we never cross the asymptote. So there is no way to reach this area over here. So we can't really have a left end behavior. Which leaves us just with the right end behavior. X approaches positive infinity because positive x values are on the right, while y approaches positive infinity because positive y values are up. Now, in some cases, you may see the left end, not really the left end behavior, but the left end described as something else. So you may see it described like this. Well, we don't go to negative infinity, but x does approach negative 2. And as x approaches negative 2, y is approaching negative infinity. This is more what you would talk about in calculus as far as limits, and not necessarily left end behavior, more of a description of what's happening on the left end of this function's domain. So sometimes places will refer to it as end behavior. I I don't, because with the definition of end behavior that's usually most readily available, it doesn't match that definition, but it is a description of what's happening on the left side or left end of the function's domain, and not the left end behavior as x approaches negative infinity. But that's a side note. So this is our left end or our right end behavior. We have no actual left end behavior. And then lastly, just describing the transformations, well, we only had one transformational rule. That was x minus 2. So if we subtract, addition and subtraction creates a translation. If we subtract 2, that's going to translate it left. Subtracting 2 from x values will translate it left 2 units. And there we have it. Okay, in this example, we're going to show that f of x and g of x are inverses. And one of the ways to show that or verify that they are inverses is using the definition of what it means to be inverses. When two things are inverses, are combined, they cancel out and form the identity. The identity for functions is the function f of x, or x. So the identity function is referred to as just x, identity function. So if these two are indeed inverses, then when we do composition, f of g of x should give me x, and g of f of x should also give me x, if these two are indeed inverses. So if I set this up, my outside one is f, so it's e to the power of x plus 1. So I'll put parentheses plus 1. Then on the inside goes my g of x, which is ln of x minus 1. Now there's nothing connected to the parentheses by multiplication or any exponents on the parentheses, so the parentheses won't really serve any purpose here. So we're going to ignore them and combine like terms, which means negative 1 and positive 1 will cancel out, leaving me with e to the power of ln of x. But e to the power and ln of x, or ln, are inverses and cancel out. So I have just x. So first side successfully verified. And since this is a show that or a verify question, it's a proof, which means every step of the way is your answer. So even if it feels like it seems kind of pointless to do, you're showing it is true and not actually solving the question, which is intended. For the other one, we're doing g of f of x, so we're going to be doing ln. G is ln, so ln of, instead of x, we'll put parentheses minus 1. Then inside my parentheses, we'll get my f of x equation, which is e to the power of x plus 1. Now we are taking the natural log of an e to the power, and natural log and e to the power are inverses, because remember, ln is log base e, and log base e and e to the power are opposites. So they will cancel out, leaving me with x plus 1. Minus 1 comes down. And then now we can cancel out the plus 1 and minus 1. We couldn't do that in the last step because the plus 1 was trapped in the exponent. But now that they cancel out, or now that there is no exponent, we just finished canceling out the 1's, leaving me with just x. So both sides have successfully shown to be x's, simplified to be x. Therefore, they are indeed inverses, and we have shown that they are inverses, which was the goal of it. Not really seeing if they were inverses, but to show it. Wow, I ran it off.